Hello, Java programmers. Let's talk a little bit about data structures. Two things that you do as a developer, a software engineer, a programmer, a coder are identify algorithms and data structures. The more you know about the data structures built in or available in your language, the better a developer you're going to be. It's worth your time to study the theory of data structures and also the application of those data structures in the languages in which you write code. There's a huge amount of overlap. If you learn about a queue in Java, you'll find there's also a queue in C# and Python and pretty much all languages because these data structures tend to model things that are in the real world. And since all programs are usually written about things in the real world, the data structures overlap. You have the opportunity when you're writing a program from scratch to figure out what the appropriate data structures might be to solve your problem. Sometimes you'll have someone else's code. You'll be tasked with the job of fixing bugs or enhancing, and you'll find that they are using built-in data structures. And again, you'll recognize those because you've studied them in the past, and you'll be off to the races. It is my theory that data structures and many computer science concepts are embodied, are modeled in a grocery store. I get a great kick out of walking around grocery stores and looking at all the things that computer science has to deal with. Maybe not in practice, but certainly in theory. So the next time you're at the store buying some chocolate ice cream, think about the queues of people waiting to check out and the stacks of 2-liter bottles waiting to be picked up off the shelf and the processes. Each person with their cart is circling through the store. They're a process, aren't they? They're filling their cart. Sometimes they're sitting idle. Sometimes they're looking at their shopping list. Sometimes they're clipping coupons. And eventually that process ends up at the front of the store. It goes through a checkout line or a self-scan. And then that process terminates when the user pays for their groceries and walks out the door. The concept of a stack is found throughout your day. You could walk through the grocery store, you could drive down the street, anything you're doing pretty much, you can find an application of a stack, which we refer to as last in, first out. I provided a couple pictures on the slide. There's a Pez dispenser. If you've ever had Pez, you've loaded it from the top, and the last one you put in, the last little Pez tablet, is the first one that pops out when you pull back on the dispenser. Last in, first out, also referred to as LIFO. Another example is the gravity feed 2-liter shelves in the grocery store. If those are stocked from the front, then the last one they shoved into that feeder is the first one that's going to be extracted by the next customer that wants a 2-liter of wonderful Mountain Dew. Now, nothing is perfect, and things aren't always what they seem. You've probably gone into the grocery store and realized that the flavor of Mountain Dew you're after isn't the first one at the end of the stack. You have to reach around behind it and pull out the second one, which would require pulling out the first one, pulling out the second one, and putting the first one back. So, strictly speaking, you violated the rules of a classic stack, but hey, that's how life is. Another stack could be envisioned as the dishes in your cabinet. if you stack them from the top and you pull them out from the top, now I tend to pull mine out from the bottom. I think I'm going to get in trouble by saying that. But you could manage that assembly of dishes in your cabinet as a stack. The last one you put on top is the first one you grab off the top when it's time to make dinner. A queue, you could call it the opposite, I guess. First in, first out, meaning whoever gets in line first will be the first person removed from that line. That is typified by the checkout line at the grocery store. If you're lucky enough to be first in line, you don't have to wait behind anyone. You get to present your coupons and your credit card. The cashier, the associate scans all of your items and you're gone. Everyone else is waiting behind you. The next person to be processed is the person right behind you, so they become first in, first out. All kinds of queues around everything we do. You queue up in traffic. The first person at the traffic light gets to be the first person through when the light turns green. Look for opportunities around you every day for queues and stacks. Another type of queue, which is used quite a bit in operating systems, is the priority queue, where some people waiting in the line are prettier or richer or have a special ticket and they can skip the line, so they have a higher priority than everyone else. And that's typified by lines at Disney World. You can buy a special kind of ticket, I believe. I've never been to Disney World. I have no plans to ever go, but I understand that if you have a special ticket, you can jump to the head of the line, which gives you a higher priority than all those sad people behind you who didn't pay as much. Inside your computer, stacks and queues are running wild. If we think about all the programs that are running, every one of those running programs, which we refer to as a process, has a program stack that keeps track of where it goes next in memory, what the values are of any local variables that it has created, and where it's supposed to end up when it's finished. And that stack contains memory addresses and also contains the values of variables. So once you understand stacks, you're working towards understanding how the operating system manages processes. Your operating system also manages queues. A great example of that are process queues, because your typical Windows computer might have 10, 20, 30, 50 processes running, not including all of your viruses and malware. But not all those processes can fit into the CPU. You might have an 8-core CPU, therefore you can only be running optimally 8 processes at a time. In order for the operating system to keep track of what process is ready to go, which ones are not ready to go, which are sitting around waiting for something else to happen like disk I/O, the operating system maintains queues. We relate to data structures by what they model and by what we can do with that data structure. What methods does it support? How do we add things to a queue? How do we remove things from a stack? Is it possible to query the queue to tell us if it contains a certain value? Is it possible to query a stack to tell us how many elements remain on that stack? Is it empty? Is it almost full? Can I peek ahead? Can I look past the first item in a queue to see what the next item is? If you're in that grocery store and you're that associate working so hard in the checkout line, can you peek past the first person to see if the second person has like 500 items and like, oh no, I have to deal with this person? Or can you just focus on the person right in front of you who is currently being checked out. So sometimes it's interesting to be able to do things with a data structure that we might not necessarily do in the classic mathematical model, but they make our programming life a little bit easier. Let's look at a queue. I have in Eclipse a simple basic project created. It has a class called main and it has a method called main. So not a lot of architectural detail here. It is a place for us to put some code and talk about it. If you think about a queue, there are three basic things that we need. Actually, only two, but we need to be able to add things to the queue. And usually we use the letter E for element or thing. We need to remove the next element from the queue. And we need to examine the element that would be next before we remove it. So sometimes it's nice to be able to look at that next element and decide whether or not it's time to actually pull it off the queue and process it, or just leave it there for some other purpose because we're not ready for it yet. Basic operations of a stack, pretty much the same except different terminology. We want to add an element to the stack, which we call push. We want to remove an element from the stack, which we call pop. So we push and pop all day long. And sometimes we want to look at that next element without actually popping it, and we call that peek. Now theoretically I could do without the peek. I could just do push and pop all day long. If I popped something and I didn't need it, I wasn't ready for it, I could push it back again and I could just do push pop all day long. The exam and the peek makes my life easier, as do a lot of other methods that are built into these data structures. There is a Java class called stack. So let's take a look at that and let's use it in some programming. Get our hands dirty here. So I am going to go back into my main and type java.util.stack. And if I refer back to my slide, it's actually lowercase j. So I'm going to have a problem right away. I'm doing this on purpose just to show you how easy it is if you don't pay attention to detail to make a mistake. It's lowercase j in java.util.stack. Java and util are all lowercase letters. Stack is capitalized at the beginning, so this needs to be a lowercase j. And then I'll just call this my stack. Let's instantiate it. We'll instantiate it in the same line where we declare that little guy. We'll say new java.util.stack. So far so good. Now you probably haven't seen me do this very often. It doesn't look quite like what we've done before when we've used library data structures. What we usually want to do is just say stack those two things we'd like to be equivalent. We'd like them to accomplish the same thing. The second one is going to give us a problem because I haven't qualified it well enough for Eclipse to know exactly what I'm talking about. Eclipse knows that there's something called stack, but it's not sure if that's the one that I'm referring to. Do I really want that stack? Do I really want that class called stack? And Eclipse offers to fully qualify that or add an import statement And that way there's no ambiguity as to what class I'm talking about. Now in line 6, I didn't have that problem because I said this is exactly the stack that I want. I want you to go to the Java library, to the util package, to the stack class, and that uniquely identifies that particular class. They both work, except in the second case I have to bring in that import statement to do it. These are two different ways of doing the same thing. But there could be a subtle got you down the road. Let's just talk about it a little bit. They both work, both of these methods work, but they may have different side effects. In line 8, there is no way that I could possibly be pointing at some other stack class. It's got to be the one in java.util. That uniquely identifies without any ambiguity where that class is defined. The second example, line 9, I'm at the mercy of whatever import statements I have provided. This is a little bit difficult to visualize because we haven't seen a problem in the past, but there could be another stack in another library. And I'm just going to make something up. Import, I'm going to say bill.util.stack. And that's just made up. That doesn't exist. But if there was another library with a stack class in it, then I could change the import statement and I could have line 10 now referring to a completely different stack class. What we learned early on is that when we're creating a computer language, there are a lot of different developers who will contribute. They all may want to have classes with overlapping names. It would be really unfair if I had to name my class like stack X in my library because there was already a class called stack. That would just be a bad deal. Rather than force people to do that, we simply allow them to qualify a name by adding a package and a library to it. And you can see then why sometimes it's a good idea to fully qualify the name when you create the variable, when you declare it and instantiate it. And sometimes it's a good idea just to use an import statement and let the import statement drive which of those you're talking about. Let me clean this up so that it does work now. And I am going to take out line 9. I'm just going to take it out. And then I'm going to put this back the way that we like it, where I just say stack here. And the import statement, whoops, I got numlock on. The import statement drives where that definition of that class comes from. So that works fine. We're still not out of the woods yet. If you hover over stack in line 8, it knows where it comes from. It comes from java.util. But in java.util, there is a parameterized stack class. So we're not meeting all the requirements of creating a stack object. Let's parameterize that and let's say that it is going to be a stack of strings. This is a parameterized class. Now I'm happy. I've met the qualifications of the parameter. I've defined where that stack class is coming from. It's coming from java.util. and I've declared and instantiated a variable. All right, can I add something to the stack? Let's say for the sake of argument, this is a stack at the store. In slide 5, we've depicted this luscious gravity feed display of sugary sweet, caffeine-infused soda or pop, depending on where you live. I think I call it pop. Let's stock one of those stacks. Each of those individual columns is a stack. The first thing you can see at the bottom of that stack, facing you as you walk up as a customer, is the top of it, or the last thing that was added to it. Therefore, if you grab it, you're doing a last in, first out operation. So let's add my stack dot, and sadly, it's not giving me my list of things I can do. So again, my help seems to be broken. But let's add Mountain Dew. It's all good. It's just that my context-sensitive help, for whatever reason, isn't functioning in Eclipse. You probably had better luck with yours. Okay, so that is the first element in that very first or leftmost column in that display at the grocery store. There's a nice green bottle of Mountain Dew. Green is certainly a naturally occurring color of pop. Let's put another one on. And the second one will be Mountain Dew. I don't know the names of Mountain Dew. Mountain Dew Caffeine Blast. Let's put another one on. And this will be Mountain Dew Red Alarm Stomach Dissolver. There's 3 things on our stack now. The question is, what will we get when we remove an item? Which of those 3 will we get when we take something off the stack? What's the terminology for stacks? Go back to the slides. In slide 12, when we remove something from a stack, we're doing a pop. P-O-P. That is the, so to speak, the general or computer science term for the stack data structure. Remember, computer scientists, strictly speaking, are not concerned with implementation in a particular programming language. They are concerned with the terminology used to describe the model. And in this case, the model is, we're modeling something called a stack, and if we want to remove something from it, we're doing a pop. Is that what I need to try in my code? I'm trying to get back to Eclipse and it's fighting with me. Come back, Eclipse. There we go. So if I say string my pop equals my stack dot pop, that seemed to work. At least Eclipse isn't complaining about it. Remove the last item added to the data structure. Is it going to be Mountain Dew Caffeine Blast, or Mountain Dew Red Alarm Stomach Dissolver? We should print that and find out, right? Now we find out together. When we run that, we see that the pop operation gave us Mountain Dew, red alarm, stomach dissolver. How about that? The next thing I'd like to know is what's left on the stack numerically. How many values are left? You'd think it'd be 2 because I popped 1. Hopefully what's left are Mountain Dew and Mountain Dew Caffeine Blast, which would be a total of 2 items on the stack. Let's add a print statement. And I want to print out the number of elements remaining on the stack. I want to know if it's empty or if there's something left. And I hope it's 2. I took off 1. There should be 2 left. In the store, you just do a visual inspection of that column and say, oh, there's 2 things left in that column. Programmatically, we need a different way. And since my help isn't cooperating today, I wonder if it is count. I'm guessing. Total guess. Well, it doesn't appear to like that. I wonder, instead of a method, is it a property? No. I wonder if it's size. Hey, that looks promising. As a programmer then, sometimes I fall back on my experience. And I know that a lot of data structures have a size property or a size method. Sometimes it's length. Sometimes it's something else entirely. But I can clean this up and make it a little prettier. Number of elements remaining. Hopefully I get 2. And hopefully I can learn how to spell remaining. 2. Good. I know what those are. What if I want to, for some reason, just empty the stack? Everybody's purchased all the pop. There's a big party coming up and there's nothing left on the stack. What if I drop into an infinite loop? And in that infinite loop, I say my stack dot pop This is a little different. I'm not assigning that value to anything. I'm popping it and then throwing it away. In the previous example, in line 14, whatever I got from pop, the pop method returned a string. I stored that string in my variable called myPop. In this case, I'm just popping. Throw it away. I don't care what it is. I just want the stack empty. Let's see what happens. There's 2 things that I'm concerned about right here. One is, since I wrote an infinite loop, is it going to run forever? There's no way to break out of that loop logically. But I'm also concerned about whether, if I pop too many things, will it just crash? If there's nothing left to pop, if the stack is empty, is it going to crash my program? Let's find out. There you go. It was the former of the 2 hypotheses. I got empty stack exception in line 19. I popped and popped and popped until there was nothing left to pop, and then my program crashed. So that's not a particularly effective way of emptying the stack if all you want to do is just pop off all the elements, because your program's going to crash. Now I could put error logic around this. Oops, sorry. I'm so used to just typing exception. There we go. That's going to catch the empty stack exception. That way I can just put a break here. The break takes me out of the infinite loop. This is a little more friendly because it will pop and pop and pop. Line 20, it'll keep executing the loop until there's nothing to pop. Then it drops into the exception handler, the catch block. The catch block executes a break statement, line 22. That takes me out of the infinite loop. There you go. We've written a set of logic to empty the stack. There we go. And it required some air handling. It required an infinite loop. It's 6 lines of code. Could be compressed a little bit, but if we lay it out nice and pretty, it's about 6 lines of code. However, based on experience, which you'll get, we probably realize that there is a built-in method in the stack class to empty the stack. It's something that you do so often that it's probably part of that class. Again, this is just something that you get the more you work with data structures. You get a feel for things that are so common that they're probably already built in. And I don't want to say that anything you might want to do to a data structure has already been done for you, but many things are. Therefore, I would go back to the documentation of that class, the stack class. I would look for a method that empties it. And that could replace all of this code I wrote right here. Don't stress out too much over that. If you wrote a little bit of code that duplicated some existing functionality, that's okay. We all do it. But just be aware in the back of your mind that you should have some time invested in the understanding or the investigation of that data structure. So let's go to Java stack class. Be very careful here because you might not get the stack in java.util. You might get somebody else's stack. You might get a stack that's in another Java built-in library. Who knows? Be careful. Well, this one says that it is from the authoritative documentation source. Oracle owns Java, therefore we can trust oracle.com. It doesn't say what library it's in. It doesn't say if it's part of java.util. We can dig a little deeper by clicking on the link, and we can see that yes, it is in java.util. That's good. That means that is the class that we're working with. I'm emphasizing this because I have had these problems in the past where I, in my program, am using a class that I didn't know was part of a third-party package, and I thought it was part of a standard Java library package. Therefore, I got very confused. That's why I'm harping on this point. We are using the correct class, java.util.stack. Our goal was to figure out if it was possible to replace all of this highlighted code with one line from the stack class. And remember, I don't have the luxury of my stack dot for whatever reason. Eclipse just isn't cooperating with me today, but that's okay. We'll just make a lesson out of it. Normally all the methods would pop up and I would search through them visually, maybe find the one that I need. But I can scan the method summary, empty, peek, pop, push, and search. And then there will be a lot of other methods that were inherited because the base class for stack is vector, which is another more general data type. If I wanted to, then I could go back and look at vector and see if it had a method for removing all the elements. That would also be available to me in this derived class. I do notice, however, that there's something called empty. Tests if the stack is empty. That means I can go back to my logic and I can say while my stack dot empty, invert that, because that method is going to return true if it's empty and false if it's not empty. Therefore, I need to invert that Boolean value. And then I don't need the try-catch logic anymore. This can go away. All I have is my pop. And my pop will run, the loop will run until empty returns true, and then that will be inverted to false. Let's make sure this works. We took out the error handling logic because it will exit the loop now when empty returns true. So it'll continue looping as long as empty returns false. This needs to go away down here. There we go. The program finished. You can see that it's not still running because that red terminate button is not lit. It doesn't generate any output underneath that while loop. Let's add a print statement at the bottom just to make sure that there are no elements left. I'll copy and paste the print statement from line 17. And it should go from 2 elements remaining down to 0 elements remaining. There we go. Good. We have replaced our logic then that depended on an infinite loop and a try-catch with a loop that continues looping until the stack reports back that it is indeed empty, and then it stops looping. It's a little bit better. We've reduced the complexity somewhat. You still have to wonder, though, is there some way to empty a stack? Because it's a common operation that you perform on a data structure. You've packed it with data, and then you realize you don't need that data anymore. And we're still doing a manual pop of all the elements. If there were a million elements in that data structure, we had to pop every one of them. That would be time consuming and processor intensive. And you have to think then that there's probably some way to empty that data structure. We see in the stack documentation from Oracle a very limited list of operations: empty, peek, pop, push, and search. That's it. But we can go backwards. We can look at the the base class for stack, which is vector, and we wonder maybe vector has a way to empty a vector, and that would be inherited by stacks, and stack is a derived class from vector, and therefore we'd have access to that method. Let's look at vector. We're still in java.util, and it's probably got some methods. It's got a whole bunch of methods. Look at that. There's add. There's clear. How about that? Removes all of the elements from this vector. It appears then that with one line of code using an inherited method, we can remove all of the elements from our stack, because a stack is a vector. Let's go back to our program again. I'm going to add my stack dot clear. I will comment out all this while loop fiddle faddle, and hopefully I'll get the same results. It will print that there were 2 items in line 17 it'll execute line 18, and then in line 26, it will print that there are no items. Let's see what we get. Good, that worked. We used, I'll just add a comment here, use a base class method that inherits into stack. What I just showed you was a strategy for determining things that you can do to a data structure by looking at the base class of that data structure. All of this would have been moot if my Eclipse help feature was functioning right now. Sometimes you won't have that though. Sometimes you'll be writing code in an environment where that luxury is not available. Sometimes you just need to learn all the things you can do by looking at the base class. Let's look at the use of the debugger when we're trying to track down information about our program. Now, we've been putting in print statements, which are fine. They sometimes have a value. It's not the optimal debugging strategy, however. You can't tell the flow of logic without adding a whole boatload of print statements and then having to go back and potentially remove them. So it's not a habit that you want to completely depend on. Sometimes you won't even have a screen. Sometimes there'll be no console, and there's no place to put print statements. Sometimes the system is so complex that when you start printing, you're going to mess up somebody else's display, or you're going to write to a device that you didn't think you were writing to. Print statements, usually for simple problems, for things you're debugging at your desk, they're okay. We still need to develop a mastery of the debugger, however. I'm going to put a debug statement right there. My line 26. Remember, if you just double click in the margin, you can set a breakpoint, or I called it a debug statement, more strictly a breakpoint. When I run in debug mode, now the program will stop there. And I just want to show you how effective it is to be able to drill down into the status, the current state of that data structure by using the debugger. I set my breakpoint, and instead of running in regular runny mode, I'm going to run in debug mode. The only difference is, at this point in our lives, is speed. The debug mode run will be slower because it has to do more intermittent processing, but it will run the same way. So if you've got a really, really large program and you spend a lot of time waiting around, then debug mode may come back to haunt you. If you got a really small program like this, you'll never know the difference. It'll be slower, but it'll be so much less slower that you won't know the difference. Click the debugger. The program builds in a debug version, which took a moment. It ran. It stopped on line 26. Line 26 is in green. That means that it has not yet executed line 26. It's waiting for us to provide more guidance. But what we want to do is hover at this point. Hover, hover, hover. I can hover over my stack. Remember, that's a stack object, and it contains 0 or more strings. And if I strategically resize that viewer window, I can look at the individual elements and I can see what's in there. I can confirm visually there's nothing left in that stack when I get to line 26. All the elements are null, which is really good now. So I've learned an effective tool for examining a variable, which I can use to replace all those annoying print statements and save myself a lot of time by adding and removing print statements over and over. Use the debugger to make yourself a much better developer. Let's kill it now. Terminate this execution. We left debug mode. We're back into just editing our code. I'll remove that breakpoint in line 26, and I will put the breakpoint somewhere else. Let's put it in line 18. Okay. Line 18 then will cause the program to stop or pause, and then we can examine the variable again. It will have something in it at this point. Let's run it in debug mode again. Da-da-da. We are sitting on line 18. We have not yet executed line 18. We can do a hover, and we can strategically grab the corner of that view window. It takes a little bit of touch. We can click on element data, expand element data. There are 2 elements in that stack right now. You'll notice that it might look a little odd because there are actually 10 elements, but 8 of them are null, uninitialized, empty. The way that Java works, when you create a stack, it automatically allocates space for 10 items because it knows you're going to add some items, and this just makes the data structure behave more efficiently. We're only using 2 of those 8 right now, or 2 of those 10 right now. You can ignore the other ones. If you were to print the size of this, you would still get 2. These are just memory locations that are currently unused. Good. Another thing you can do with the debugger is you can right-click on that symbol on my stack, and you can say watch. That creates another window in your Eclipse IDE, and I guess I wasn't clicked on it yet. Let's try it now. Right click, watch, there we go. That tells you the current status of all the elements in the stack, and it shows you only those 2 that are used up. The other 8 it doesn't bother with. And that window persists, so you can step through the code and watch these values change as you run the program. So it's a kind of a more persistent way of doing the hover. It's called they call it an expressions window. Sometimes it's called a watch window. If you're doing serious debugging and it's getting complex, you may have several different variables in that watch window. You can see how they change as the program progresses. Take the time, learn how to use the debugger. It will make you a much more efficient developer, and you'll get done early and you can go outside and play. To wrap up this discussion, I will just point out that the queue is implemented in Java as an interface, not as a class. If someone asks you to create a program with a queue in it, you have to find a built-in Java class and that uses that interface. The interface is called queue, Q-U-E-U-E. You can create your own data structure that acts like a queue. All you have to do is implement that interface, and then everybody knows how to talk to you. The easiest one is going to be the class called linked list. So in Java, a linked list behaves like a queue. In computer science, a linked list is one of the first things that data structure students learn. We're not going to spend any time on it here because it's already implemented for us in java.util. But in computer science, we would spend a semester, I'm exaggerating a little, we would spend a long time studying the behavior of linked lists and implementing them and figuring out whether they were efficient or not. It's actually one of the most common asked questions, it seems like, on Reddit and Stack Overflow because computer science students are so often given the job of writing a linked list. There is another difference between computer science and IT, or computer science and programming. A developer who's programming for a living is extremely unlikely to be required to write a queue or a stack, but is likely going to be asked to use them because they've already been implemented. If you want to write your own stack, start from scratch using just native types like strings and ints. It's a great exercise and it will teach you a lot. It's just not something that we do in practice. Why would I ask you to create a new stack class when there already is a stack class? A difference between computer science and programming. I hope that was interesting. Thank you very much. Bye bye.